Welcome. So, we are discussing about the isoperimetric problem in the last lecture, and the statement what we wanted to prove is that if we take a simple closed curve for C 1 and then with the fixed perimeter, fixed length, arc length fixed, then what we among all those curves, the circle is going to have the maximum area. So, in other words, this what it says that if L is the length, then this inequality holds. A is the area is less or equal to L square by 4 pi, and this inequality is called the isoperimetric inequality. Okay. So, and then the equality holds if and only if gamma is a circle. So, now let us look at the proof. So, we can it is enough to prove for L equal to 1, otherwise we can change just by the parameter. Okay. So, gamma is closed, therefore, x and s they are the function from 0 to 2 pi to r, and 0 is equal to 2 pi, x of 0 is equal to x of 2 pi, because x 0 y 0 this is equal to x 2 pi y 2 pi. So, it is a closed curve means that. So, now x 0 is equal to x 2 pi. So, we can think of this as a function on this, and which is a 2 pi periodic function. So, once we have got 2 pi periodic function, then we have the full power of the Fourier series to employ. So, therefore, the Fourier series of x s is a n e to the power I n s and y s b n e to the power I n s, where a n is the Fourier coefficient of x and b n is the Fourier coefficient of y. So, now if I take the derivative, then because it is a C 1 curve, so x is in C 1, we know that the Fourier series converges absolutely. So, we can do the term by term differentiation. So, by differentiating with respect to s, we get this is a n I n e to the power I n s and y prime of s b n e to the power I n s. Now, as you can see that in order to find the L is always given in terms of x prime and y prime. So, by Parseval identity, so now mod of n square a n square, so this is equal to, so Parseval identity says that mod of n square mod of a n square, this is equal to integral over mod of x prime of s square ds. So, now this is the L2 norm. So, this if I take the parameterization arc length parameterization, so this is going to be equal to 1. So, this is what we have got. So, equation number 1 is n mod n square plus mod a n square plus mod b n square is equal to 1. Okay. So, remember that x, both x and y as a map, they are real map. Therefore, x s bar is equal to x s and y s bar is equal to y s. So, therefore, x s bar if I take, then the Fourier series is going to look like a n bar e to the power minus of I n s. So, because x s bar is equal to summation over n a n e to the power I n s bar. If I take the bar this side, because it is real, this is x s. So, therefore, a n bar e to the power minus I n s. Similarly, the Fourier series of y s bar is this, and y s bar is equal to y s. So, these two are equal. So, therefore, by the equality we will get the excess on the other hand, we have a n e to the power I n s, and so now excess bar, this one I can write this as summation over n a minus of n bar e to the power I n s, because n is varying over z. So, I just make a change of variable from n to minus of n, and this is also I can rewrite this as b of minus of n bar e to the power I n s. Now, if this and this are compared, then we get a n equal to a minus of n bar and b n equal to b minus n bar. And look at the what we know, the area is given by 1/2 of the modulus of 0 to 2 pi y prime s x s minus y s x prime s d s, and which by the Parseval identity. So, this is what is that what we know in the Parseval identity is x y as the function. This is going to be the x hat of n, y hat of n bar. Therefore, this is 1 by 2 pi. If you want to write 1 by, this one is 1 by 2 pi integral 0 to 2 pi x s y s bar d s. So, now if I replace y by y prime, then what you are going to get, as you recall that the y prime Fourier series, what we had seen is that I n b n e to the power I n s, that is what the Fourier series is. Now, if we have a bar there, you are going to get the bar, and both the I factor is going to come out. So, therefore, mod is going to kill your I. Therefore, what you left with for this n a n b n bar, because this is real valued. So, y prime of s bar is equal to y s, and then this is b n minus a n bar. Okay. So, what we know is that a n b n bar minus b n a n bar, this is less or equal to, just by simple triangle inequality, this is less or equal to twice mod of a n into mod of b n, because this is less or equal to this mod plus this mod, and mod goes bar is goes away. So, this is mod of a n minus plus b n, and which is less or equal to by the geometric mean and arithmetic mean. So, this is going to be less or equal to mod of a n square plus mod of b n square. Okay. So, now what we know is that mod of n is less or equal to mod of n square, because n is varying over z. Therefore, mod n is this. So, now a is less or equal to, what we have seen is that this is mod n mod of a n square plus mod of b n square. Now, this is again less or equal to, because mod n is less or equal to mod n square. So, this dominates this. Now, this, as you can see, that this we have by the Plancherel formula, what we have said that this is equal to 1, because this is the mod of x prime of s square plus mod y prime of s square, and which we have taken it to be equal to 1. The L2 norm of that is equal to 1. So, then this becomes pi. So, therefore, that is what essentially we wanted to prove, that A is less or equal to pi, because we are taking we have done this. Now, for the equality, now if A is equal to pi times summation over n varies over z mod n mod of a n square plus mod of b n square, which is equal to pi times mod of a n square plus b n square times mod n square, which is again equal to pi, because you see in the previous one what we have seen is that these are all the inequality. So, now if the equality happens, suppose this is given to be pi, then what happens is that all this intermediate inequality, they will become equality. Now, this tells us that this is all this is equal to this. Now, as you can see, if mod n is not equal to 1, minus 1 or 0, then mod n is going to be strictly less than mod of n square. But now, however, we are saying that this equality happens, therefore, the a n and b n, they are 0 if mod n is greater than 1, that means if mod n is greater or equal to 2. If it is non-zero, then we can't say that this inequality is equality is going to hold. Only possibility is that n equal to 0 or and n equal to 0, this vanishes. So, n equal to 1 and minus 1. So, therefore, x s, this is equal to a minus 1 e to the power minus I s plus a 0 plus a 1 e to the power I s. So, in the Fourier series, a n's are 0 of x, the a n's are 0 for n mod n greater or equal to 2. So, now the Fourier series of x s becomes this. So, this is a trigonometric polynomial which will look like this. Similarly, the y s will look like b minus 1 e to the power minus of I s plus b 0 plus b 1 e to the power I s. Therefore, as we have already noticed, we have observed that a 1 a n is equal to a minus n bar, when because x is a real valued function, then equating both we have got this relation, and b 1 is equal to b minus 1 bar. So, therefore, what do you get over here? And we have 2 mod of a 1 square plus mod of b 1 square is equal to 1. Also, we have the geometric and arithmetic mean. So, now all in the equality, every inequality becomes the equality. Therefore, what we get is that equality of g m and a m, we get mod of a 1 is equal to mod of b 1, which is equal to 1/2. Okay. So, then obviously, this is lying on the circle of the radius half. So, this a 1 is 1 by 2 e to the power I alpha, and b 1 is equal to 1 by 2 e to the power I beta for some alpha and beta. Now, already we know that a 1 b 1 bar minus b 1 a 1 bar is equal to 1/2. That is in our calculation what we had seen, and then this will imply that this mod a 1 b 1 bar is equal to 1/2 e to the power minus of I alpha, then e to the power I alpha e to the power minus of I alpha. So, this is 1 by 4 e to the power I alpha minus beta minus 1 by 4 e to the power I minus I alpha minus beta. So, this mod is equal to 1 by 4 into 2 I mod sin alpha minus beta. So, this is nothing but this is equal to 1/2. So, this is 1/2 goes away. So, this means I am going to get that mod of sin alpha minus beta is equal to 1. So, if this is 1, then we can say that alpha minus beta is going to take plus or minus some odd multiple of pi by 2. So, this is 2k plus 1 pi by 2. So, therefore, x s, which is equal to, if we put the value of s remember that what is our excess? This is a minus 1 e to the power minus of I s plus a 0 plus a 1 e to the power I s, and therefore, if we add this to a minus 1 is a 1 bar, and so what you are going to get that this is nothing but a naught cos alpha plus beta, and similarly y s depending on the parity of the k, this is going to be b naught plus or minus sin alpha plus s. Nevertheless, in either of this case x minus of a naught square plus y minus of s b naught square, this is going to be equal to 1, and that is nothing but a circle. So, this proves the isoperimetric inequality that in a simple closed curve with the fixed length, then this is going to be always less or equal to L square by 4 pi, and the equality will hold only if and only if it is a circle. So, that means so circle is the curve which encloses simple closed curve C1 curve which encloses the largest area. Okay. So, that is one application of the isoperimetric problem. So, now I would like to have another application of the Fourier series. Okay. So, now this is a bit of a number theoretic application what we are going to discuss. So, for that let us define, if I take a x is in R, then all of us we know what do we mean by bracket of x. This is the largest integer less or equal to x. Now, I denote the fractional part of x is denoted by x, which is x minus bracket of x. As you can see that this clearly belongs to the closed 0 1 open interval. That means, wherever suppose this is 0 1 2 like this, suppose I have a 1.3 here, then the fractional part is going to be here. So, we define another relation on R is that x is related to y, where x and y they belongs to R, if so, which means if x minus of y, this belongs to z. That means 1.3 and 16.3 they are related. So, now because the in other words what I am saying, you take the fractional part of x and you take the fractional part of y, then they are going to be equal, then I will say that x is related to y. Of course, x is related to x and y, if x is related to y, then y is related to x, and if x is related to y and y is related to z, therefore, then x minus of z is equal to x minus of y minus of z minus of y. So, now this is an integer and this is an integer, the difference of the two is an integer. So, therefore, this is an equivalence relation. So, one can actually construct the equivalence class in terms of the fractional part of a number. So, which means if I take a number between 0 and 1, it has its own representative between 1 and 2, 2 and 3, 3 and 4, like this. So, this is essentially a kind of, if you push with the integer, if you add on, so you are going to get infinitely countably many points of this corresponding to this number between 0 and 1. Okay. So, now I take a number, suppose gamma, this is in R. Now, I consider the sequence of fractional part of n gamma. Now, this sequence, this belongs to 0 1 for all n belongs to z. So, what then I consider this sequence n gamma, that is, let us write it down. So, this is fractional part of gamma, fractional part of 2 gamma, fractional part of 3 gamma. If I am taking just the n in n, if you 1, 2, 3, 4 like this. Okay. So, now let us say I consider this sequence. Now, is it necessarily true that this sequence first of all is going to be an infinite sequence, which means there will not be any repetition, there will be infinitely many distinct numbers in for every gamma belongs to R. For example, let us take first that gamma is equal to p by q. Then the first one I will write p by q, fractional part. The next one I will write 2p by q. It goes on, let us say q minus 1p by q, and then qp by q. Now, qp by q is nothing but this is equal to fractional part of p, which is equal to 0. So, now when we are going to start again, suppose q plus 1 p divided by q, if I take the fractional part here, then this is going to be the fractional part of p plus p by q, and then this is nothing but the fractional part of p by q, which you are landing off here. And q plus 2 if you take, then you are going to land here. So, now this is going to repeat after every q. Therefore, this can only take the value from this to this. So, this is not an infinite number. Now, what about if gamma is irrational? If gamma is irrational, then let us say suppose n1 of gamma fractional part, this is equal to n2 of gamma. So, can this be possible? Now, as you can see that if the fractional part they are equal, then we know that this n1 gamma is congruent to n2 gamma, because n1 gamma minus of n2 gamma, this is because n1 gamma is integer part of this plus fractional part of n1 of gamma, and n2 gamma, this is equal to integer part of n2 gamma plus n2 of gamma. Now, if I take that difference n2 gamma minus of n1 gamma, this is equal to n1 gamma n2 gamma minus the integer part of n1 of gamma, this belongs to z. Therefore, n2 gamma minus of n1 of gamma, this is equal to k, where k is some integer. This will imply, suppose if n1 is not equal to n2, if n1 is not equal to n2, then gamma is equal to k by n2 minus of n1, which belongs to Q, but we have started with an irrational number. So, therefore, for any irrational gamma, n gammas, they are distinct. Hence, we have an infinite set, countable, it is a sequence, infinite sequence, and how densely they are inside this interval 0 1. That is what we will see is that in fact, this sequence is dense in 0 1, in the sense that you take any interval a b, then there will exist one such element there. As a matter of fact, we will prove much more than this in the next lecture. Thank you.